First of all, let's try to understand what projectile motion exactly is. Motion in 2 dimensions under constant acceleration is termed as projectile motion. So in the previous chapter we studied about motion in a straight line. Remember? In this chapter we are going to study about motion in 2 dimensions. Motion is occurring along the x-axis as well as along the y-axis. When this motion occurs with constant acceleration, then the motion is projectile motion. Take a look at the motion of this ball here. If you project this ball up in the air at a certain angle with the horizontal, this will be the path of the ball. Take a look at the path once again. Basically, this ball has been projected up from the ground with a velocity u at an angle theta with the horizontal. The horizontal axis is the x-axis and the vertical axis is the y-axis. The acceleration due to gravity that acts on the ball is constant. Therefore, the motion of this ball is projectile motion. So basically, if you throw any particle at an angle to the surface of the earth, the motion of that particle will be projectile motion. Understood? That's because the motion will not be along the x-axis, the surface of the earth, or along the vertical direction. Isn't it? It will be along both the x and the y-axis. The acceleration in the case of projectile motion is vertically downwards. As you know, the acceleration due to gravity is vertically downwards. So in this case, how do we solve problems? How do we find out what the velocity of the ball or the stone after some time is? How do we find out how much vertical distance the ball has covered or how much horizontal distance it has covered? Well, what we basically do in this case is we resolve the velocity of the ball in 2 parts. We resolve it along the x-axis and we resolve it along the y-axis. If you look at the initial velocity of the ball, the component of this velocity along the x-axis is u cos theta. The component of this velocity along the y-axis is u sin theta, isn't it? So we resolve the velocity along the x and y-axis and then we apply the equations of motion. V equal to u plus at, v square is u square plus 2as, s is ut plus half at square in the vertical direction and in the horizontal direction separately. Understood? So basically we resolve the velocity along the x-axis and along the y-axis and then we apply the equations of motion along the x-axis separately and along the y-axis separately. Let's first find out what happens to the particle's velocity that's parallel to the x-axis. You see, when this particle is projected, there is no acceleration or deceleration along the x-axis, isn't it? The only acceleration is vertical. It's along the y-axis. Therefore, the velocity of a projectile along the x-axis does not change. The initial horizontal component of the velocity was u cos theta. If you look at the ball after some time, the horizontal component of the velocity will still be u cos theta. If you look at the motion of the ball after some more time, the horizontal component will again be u cos theta. If you look at the horizontal component of the velocity of the ball when it touches the ground, again the velocity will still be u cos theta. The reason for this is that there is no acceleration along the x-axis. So why should the velocity change along the x-axis? It doesn't change. So this is one very important fact that you must remember. The horizontal component of the velocity of a projectile does not change. It always remains u cos theta, where u is the initial velocity of the projectile. As you can see, ax, the acceleration along the x-axis is 0. Vx, the velocity along the x-axis is u cos theta. Sx, the distance covered along the x-axis by the projectile is u cos theta into t. You see, we know that when there is no acceleration, distance is speed into time. Therefore, the distance covered by the projectile along the x-axis is the velocity along the x-axis into the time taken. So Sx is u cos theta into t. Understood? So if t here represents the net time taken by the projectile, in flying through the air and coming back to the ground, in that case Sx here or u cos theta into t here represents the net horizontal distance covered by the projectile. If you take this point here, then u cos theta into t tells us the net horizontal distance covered by the projectile up to this point. If you take this point here, then u cos theta into t tells us the net horizontal distance covered by the projectile up to this particular point. Understood? So this is something you must remember. What about the vertical direction? We can similarly apply the equations of motion in the vertical direction. In the vertical direction, the initial velocity of the projectile is u sine theta. Well, the velocity in the vertical direction is u sine theta. However, the acceleration due to gravity is acting in the vertical direction. So u sine theta does not remain constant. It changes as the projectile moves along its path. We know that v equal to u plus at. Applying this equation in the vertical direction, we get the velocity after time t1 as u sine theta minus gt1, isn't it? U sine theta is u, the initial velocity in the upward direction, minus g is the acceleration in the downward direction, t1 is the time elapsed after the projectile has been released. So after time t1, the projectile will have a vertical velocity u sine theta minus gt1. After time t2, the projectile will have a vertical velocity u sine theta minus gt2. As you can see, the velocity of the projectile is constantly decreasing. After time t3, when the projectile finally reaches the ground again, it will have an upward velocity u sine theta minus gt3, isn't it? So basically, we have resolved the velocity in two directions, x-axis and y-axis. The velocity along the x-axis for the projectile remains constant, and the velocity along the y-axis is u sine theta minus gt at any time t. This is quite simple, isn't it? So this is one fact that you must remember, that in case of projectile motion, we resolve the motion in two directions and then we apply the equations of motion along the x-axis and along the y-axis. As you can see, Ay, the acceleration along the y-axis, is minus g because it's g downwards. Vy, the vertical velocity, is u sine theta minus gt at any time t. The displacement along the y-axis at any time t is u sine theta t minus half gt square. You see, if we apply the equation s equal to ut plus half at square for the projectile in the vertical direction, then the initial velocity is u sine theta, the time is t, the acceleration is minus g. Therefore, sy is u sine theta t minus half gt square. At any instant, t, if you want to find out the height of the projectile from the ground, then you can easily find it by applying this equation. U sine theta t minus half gt square is the height of the projectile at any instant. Understood? So this is very important. Now we can look at the motion of the projectile, both along the x-axis and along the y-axis. At any instant, the projectile will have a velocity v. If we resolve this velocity v along the x-axis and the y-axis, then we will see that the velocity along the x-axis will still be u cos theta. After all, the velocity along the x-axis is constant, as there is no acceleration in the x direction. The velocity along the y-axis will be u sine theta minus gt1. The net velocity of the projectile at any instant is square root of u cos theta whole square plus u sine theta minus gt1 whole square. Understood? After all, if there are two perpendicular components of any velocity vx and vy, then the magnitude of the velocity is square root of vx square plus vy square. So you can basically determine, the net magnitude of velocity of the projectile at any point by squaring the two components, of the velocity u cos theta and u sine theta minus gt1 and taking the square root of this expression. You can similarly calculate for the entire motion of the projectile, ax, or the acceleration along x-axis, is 0 and the acceleration along the y-axis is minus g. The displacement along the x-axis is u cos theta into t, while the displacement along the y-axis is u sine theta t minus half gt square. There you go. These are the basic expressions related to projectile motion. Actually, all you really have to do is, you have to resolve the velocity of the projectile along the x-axis and y-axis. Then you have to treat both these velocities separately. You have to write equations along the x-axis, write equations along the y-axis. You will get answers in terms of the component of the net displacement of the projectile from its initial position along the x-axis and along the y-axis. Similarly, you will get the velocity of the projectile along the x-axis and along the y-axis. So this is what you should do. Another fascinating term associated with projectile motion is the trajectory of projectile motion. If you remember, in the last chapter we had learnt that the term trajectory basically refers to the relationship between the y coordinate and the x coordinate of a particle moving in 2 dimensions. A projectile is a particle moving in 2 dimensions. What is the relationship between the y coordinate and the x coordinate of a projectile? Let us consider, a projectile at any general point on its path, here, where this cross is located. So you can say that time t has elapsed after the projectile has been projected up in the air. At this instant, the x coordinate of the projectile is clearly u cos theta into t. There's no doubt about it, is there? We just discussed that displacement along the x-axis is u cos theta into t. The y coordinate of the projectile is u sin theta t minus half gt square. Now what we can do is, we can substitute t from the first equation in the second equation. We can substitute t as x divided by u cos theta in the second equation, the expression for y. When we do that, we will get a relationship between x and y. That will be the trajectory of projectile motion. The trajectory of projectile motion after substituting t from the first equation in the second comes out to be this expression. You must remember this expression for the trajectory of projectile motion. Y is x tan theta minus g secant square theta divided by 2u square into x square. So basically this is the relationship between the x coordinate and the y coordinate of a projectile. Theta here refers to the angle of projection, that is the angle that the initial velocity of the projectile makes with the x-axis. Understood? So this is the equation of the projectile's trajectory. Note that the equation y equal to bx plus cx square refers to the equation of a parabola. Therefore, the equation of a projectile is also a parabola. After all, you can see that this equation is of the form y equal to bx, where tan theta is b, plus cx square, where c is minus g secant square theta by 2u square, isn't it? So therefore, the equation of a projectile is a parabola. If you join all the points on the path of the projectile, you will get a parabola. This also means that this blue path of the projectile shown on your screen is actually the equation of a parabola. So there you go. This is another important fact about projectiles. Now that we've understood, how to calculate the velocity of a projectile after time t, the displacement of a projectile along the x and y direction after time t, let's try to calculate a special expression, the time of flight of a projectile. The time of flight of a projectile refers to the total time taken by the projectile in coming back to the ground. Understood? So for example, if a projectile has been projected from the ground into the air at time t equal to 0, and if it lands back on the ground at time t equal to capital T, then capital T will be the time of flight of the projectile. It will be the time in which the projectile reaches here, back to the ground. How can we calculate this time of flight? Very simple. You see, we can apply the equation of motion s equal to ut plus half at square in the vertical direction. When we do that, we can say that sy, or the height of the projectile at any time t, is the initial vertical velocity of the projectile into t minus half gt square, isn't it? After all, the acceleration is minus g and the initial vertical velocity of the projectile is u sin theta. We are assuming the upward direction to be positive. Now the time t will be equal to the time of flight when the net vertical displacement of the projectile is 0. After all, when the projectile strikes the ground again, its net displacement from its initial position along the vertical direction will be 0. So sy is 0. 0 equal to u sin theta into capital T minus half g into capital T square. Here capital T refers to the time of flight of the projectile. On simplification, the time of flight comes out to be 2u sin theta by g. This is again an expression that you must remember. The time of flight of a projectile, or the time taken by the projectile which has been projected from the ground to reach the ground again, is 2u sin theta by g. Here u is the velocity with which the projectile is projected, and theta is the angle that the initial velocity of the projectile makes with the x-axis. Understood? So this is an important expression you must remember. Let's look at another interesting concept, the maximum height reached by the projectile. This is the maximum height reached by the projectile. You can see that the height of the projectile initially increases, and then after attaining the maximum height, the projectile starts descending and finally it reaches the ground. What is the value of this maximum height? We can again find this maximum height by applying the equations of motion. We know that v equal to u plus at. V in the vertical direction is u sine theta minus gt, because u sine theta is the initial velocity in the vertical direction. Now when the projectile attains its maximum height, its vertical velocity is 0, isn't it? After all, if its vertical velocity was not 0 at its maximum height, then the projectile must have gone still higher up. If it stops going up after the maximum height, that means that the vertical velocity of the projectile becomes 0 when it reaches its maximum height. After crossing this maximum height position, the velocity of the projectile gets inverted. Understood? It goes up until it reaches its maximum height, then it comes back down. So Vy is 0 if we are talking about the maximum height. If t1 is the time in which maximum height is attained, then clearly t1 is u sine theta by g. Now we can apply the equation s equal to ut plus half at square in the vertical direction to obtain the value of this maximum height. Sy is u sine theta t minus half gt square, but t is u sine theta by g. Substituting the value of t in this equation, we get the value of the maximum height attained by the projectile as u square sine square theta by 2g. Understood? This is another very important expression that you must remember. If a projectile is projected with a velocity u at an angle theta to the ground, then the maximum height attained by the projectile will be u square sine square theta by 2g. Understood? There you go.